So if your pen or pencil breaks, it can be annoying. If a part of your car breaks, it can be expensive. If a part of an airplane or building or bridge breaks, it can be absolutely catastrophic. There are several technologies that have been invented to detect the signs of failure before they occur and prevent these kinds of catastrophes. One of the common techniques is X-ray, where they'll literally X-ray the parts, and a technician will look through the X-rays for cracks to see if they can identify a breakage. Other common methods are to trap the flow of electricity or heat through a material, and they can identify cracks by where that flow is interrupted. A really popular method is to take the part of interest and immerse it in a fluorescent dye, the idea being that the dye will get caught in the cracks and make it easier for a technician to identify. Now, these methods save a lot of money and lives, but there are shortcomings. In particular, there are ways that materials can be damaged that don't necessarily cause cracks. One example of the way the material can be damaged would be if it feels a large amount of load over a short period of time, like a building would experience in an earthquake or an airplane in an extreme maneuver. Another example would be chemical changes that can occur in the material, like rust, or much harder to detect, a process called sensitization in naval-grade aluminum. This change occurs slowly over time, and it can lead to massive failures of the material. In fact, right now the US Navy spends over $60 million a year just repairing the damage from sensitization in aluminum, and that's expected to double in the next 10 years. What we're working on is a way to fill in these gaps, to detect these kinds of damage so that you can prevent more failures. And what we're using to do that is a special property of light. You see, if you take a lot of light and you shine it onto some materials, like aluminum or steel, a small amount of that light will actually reflect off as a different color. And what we found is that you can look at how much this different color, it changes in this different color, and how much is coming off the material, and use that to detect changes in the material. For example, in naval-grade aluminum, as the amount of sensitization increases, the amount of this other color that reflects off of it also increases. So we've been able to identify a material that has a little bit of sensitization, but is still sound, a material that has enough sensitization that it's at risk for imminent failure. We've also been able to, we're also right now starting to map large loads on aircraft-grade aluminum, and how this other color of light, how much of that reflects off, and depending on how much load the sample's experienced. And that's it.